Good morning, dear students. Today we are going to discuss about coordination chemistry. Already we have discussed so many topics, and I have sent so many videos regarding valence bond theory, crystal field theory, how the splitting of d orbitals takes place in the presence of ligands. And if in the case of octahedral, what is the splitting? That is T2GEG. And if in the case of tetrahedral complexes, the splitting is as E and T2. We know what is T2G, dxy, dyz, dxz. Eg means dx square minus y square dz square. The energy of T2G is actually splitting is greater than delta O. And the energy order is Eg orbitals are having highest energy in the crystal field splitting of octahedral cases. In the case of tetrahedral case, E2 will be having higher energy than the E11. That means T2G and E orbitals are in the ground state level where electron occupies first. Then CFSE not only in the octahedral and tetrahedral, we also have seen in the case of distorted octahedral what is the in the case of distorted octahedral, greater the repulsion, greater the energy. We have mentioned energy of the CFSE. That means dxz is equal to dy z is less than dxy is less than dz square is less than dx square minus y square. That means dx square minus y square is the orbital which is having highest amount of energy in the case of distorted octahedral. In the case of square planar also we have seen that in the case of square planar also dx square minus y square only is having highest amount of energy. Here interchanging takes place between the dz square and dz square and dxy. The order of the CFSE we have seen that delta t is greater than less than the delta t is less than the delta O, delta T is equal to 4 by 9 delta O, delta SP is less than greater than the delta O, delta SP is equal to 1.3 delta O. That means in this order you can see that delta SP will be greater than the delta means CFSE, crystal field splitting energy. Okay, delta SP is greater than the delta O is greater than the delta T. Okay, delta T. Now CFSE is that each electron occupying in the T2G orbitals in the octahedral case will have minus 0.4 delta O. That means each electron in the octahedral complexes in the T2G level, the presence of an electron in the T2G level will stabilize the complex to the extent of 0.4 delta O or minus 0.4 delta O or 0.4 dq. Okay. If this same thing is converted, it can be 0.4 dq. Same way, each electron in the EG level, the presence of an electron in the EG level destabilize the complex to the extent of 0.6 delta O or 6 dq. Okay, now we are going to see different factors that are affecting the magnitude of splitting. We know that already in an isolated gaseous state, the 5d orbitals are degenerate. They are of equal energy. As the ligands are approaching, their energy increases. So they are in their excited state. But completely in the presence of ligands, when the ligands are approaching completely and coming to form a bond with them, then the orbitals are splitting into two different energy levels. They lose their degeneracy and split into different levels. That is splitting only we have mentioned here. In the case of an octahedral, it is splitting as T2GEG. In the case of tetrahedral, it is E and T2. In the case of distorted tetrahedral, this is the splitting. In the case of square planar, this is the splitting. So now what are the different factors that are affecting this splitting? Okay, the first factor is geometry of the complex. The first factor is the geometry of the complex. How the geometry of the complex is helping for the magnitude of splitting to become more. The degree of splitting of d orbital is affected by the geometry of the complexes that we have already discussed. That is why delta Sp is greater than delta O is greater than delta T, where Sp is the CFSE of the square planar complexes, delta O is the CFSE of the octahedral complexes, delta T is the CFSE of the tetrahedral complexes. We know that delta Sp is equal to delta Sp is about 1.3 times of delta O. Delta Sp is equal to 1.3 times of delta O, whereas delta T is 4 by 9 delta O. 4 by 9 delta O. So geometry of the complexes. The complex is forming a square planar complex. The CFSE will be much higher than the complexes. CFSE of the octahedral complexes, that will be higher than the CFSE of the tetrahedral complexes. Okay. Then next one is the oxidation state of the central metal ion. The next factor which is affecting the magnitude of splitting means this is the magnitude of splitting. This splitting is called, okay, this is the magnitude of splitting. Okay, this is splitting factors only now we are discussing. The first one is the geometry of the complexes, and the second one is oxidation state of the central metal ion. Next one is oxidation state. The charge on the central metal ion has a direct effect on the magnitude. Charge of the central metal ion. We always know that the complexes are formed with the central metal ion. The complex has a central metal ion, a positively charged central metal species. Ligands are negatively charged species, and they come and form a coordinate covalent bond, and that's why coordination complexes are formed. Now, if the charge on the central metal ion increases greater, suppose as I mentioned to you that the charge on the central metal ion is always positive charge. It is an electron deficient, vacant d orbital. It has got vacant d orbitals. So what happens if it is a plus charge, plus 1 means a little positive charge. Okay, minimum attraction can take place between a ligand and the central metal atom. Suppose this same metal has a plus 2 charge, the attraction between the ligand and the central metal will be little more. And if it has a higher charge, maybe plus 3 or plus 4, what happens here? The attraction between the electrostatic force of attraction between the negatively charged ligands and the positively charged metals will be high. So higher the charge of the central metal ion and greater will be the attraction of the ligands. Hence the ligands will be drawn more closely to the central metal atom. Hence ligands will be drawn more closely to the central metal atom. How these ligands are drawn? Okay, ligands are electron rich species. So if it has a highly positive charge, the negatively charged ligands will be attracting more easily. So as a result, the attraction will be more. Hence the ligands are drawn more closely to the central metal atom or central metal ion, and they will have greater effect in perturbating the central metal d orbital. they will forcefully they come with a lot of energy, with a lot of attraction. Attraction has always an energy, isn't it? So what happens? Attraction, greater effect will be perturbing the metal d orbitals. This leads to higher d value. So here what happens? Greater the charge of metal ion, greater will be attraction, and greater will be the magnitude of splitting. So delta value will be very high. Theoretically, what happens if a central metal atom is shifting from metal +2 state to +3 state, it should increase. Ionic charge should result in increased value of, theoretically the magnitude should be increased to 50%. Suppose +2 state, it has an amount more than 50% when it comes to the +3 state, that magnitude of splitting should increase. But theoretically it is increasing only 40%, because when ligand comes with their electrons, metal d orbital also contains electron. So there will be a possibility of the increased interelectronic repulsions. Increased interelectronic repulsions will be the reason when it should have a 50% of maximum increase, it is showing only 40%. The 10% is decreased because of the interelectronic repulsion. So oxidation state of the central metal ion, we know that metal is a positively charged species. It is an electron deficient ion, and it keeps ready vacant d orbital for the ligands to come and form a coordinate covalent bonds. Okay, so but what happens as the metal charge increases, great will be the attraction between the negatively charged ligands and the positively charged metal ion. And when the attraction is more, greater will be the splitting. Usually if a metal is coming from +2 positive state to a +3 state, the magnitude of splitting should be 50% increased. But it is increasing only 40%. That is because of the interelectronic repulsion. So we know that. So metal greater will be the positive charge, greater will be the splitting of the magnitude splitting. Next one is we are going to see is another important factor which is influencing is principal quantum number. All of us know from 8th standard, from our basic studies onwards, we have known what is principal quantum number. It is the main energy level. It describes the main energy level in which the electron is residing. Generally, the crystal field splitting is the greatest for complex in containing 5d electrons. Always the magnitude of splitting will be very high for the 5d electrons. Okay, then 4d electrons, then only 3d electrons. So this is due to the why this magnitude of splitting is high. Magnitude of splitting means this splitting is very high. Okay, for 5d electrons. Why this splitting is very high is because the 5d orbitals are extended farther into the space and hence interact more strongly with the ligands. When you come to the 3d orbitals, suppose if you take 3d orbitals, the d orbitals are very closer to the central metal atom. Okay, the positively charged species. So as a result, the attraction can be very low. Okay, but what happens if 5d orbitals means 5d orbital means they are farther, they are away from the positively charged nucleus. They are away from the positively charged nucleus and they interact more strongly with the ligands. More strongly with the ligands. So this increases the amount of splitting. This increases the amount of splitting. So usually in the case of 5d orbital, since the splitting is maximum, the fourth electrons, suppose if it has a, if it is a d4, or d5, the fourth electron will not go to the e orbitals or eg state, it will be pairing up here because the magnitude of splitting is very high. For the energy required for the electron to go into that much e orbitals is not sufficient. So automatically in the 5d series, most of the complexes are low spin complexes. It's a very important factor. You should remember that in the principal quantum number increases the magnitude of splitting. Okay, so here we know that what is the main transition elements only are participating in the ligands. They belong to the D block elements. They are of 3D series, 4D series and 5D series. And we know that 3D, 4D, 5D, when you say, that describes the quantum number of the electrons. So 5D orbitals have a magnitude of splitting is very high. That means the distance between the T2G level and EG level becomes very high. So the fourth electron to enter into the EG level, that energy is not sufficient for an electron to enter into the EG level. So automatically the electron pair up in the T2G level. That is the reason why most of the cases, not most of the cases, mostly all the 5D complexes are low spin complexes. All the 5D orbitals are the low spin complexes. The same happens with the 4D. In the 4D also the magnitude of splitting is very high. So the fourth electron will not enter into the EG level because of the energy barrier is very high. So it also will pair up. So please remember an important point is here that most of the probably maximum most of the 5D complexes and 4D complexes form only low spin complexes. That means electron pairing takes place. Electron pairing is taking place. Okay, only 3D series only we have a complexes of low spin and high spin. Complexes of low spin and high spin. Okay, that depends upon the nature of the ligand. So I suppose you understood this one. Okay, and the important, since the nature of the ligand is the one which is helping this magnitude of splitting, means the next factor will be the nature of the ligand. Next factor is nature of the ligand. Okay, the nature of the ligand also will affect the magnitude of splitting. Okay, how it is splitting of d orbitals. The ligands having less splitting ability. The ligands having a less splitting ability are called ligands less splitting ability. D orbital splitting are called weak field ligands. And the greater splitting power, if the ligands are having greater splitting power or greater splitting ability, they are called high field or strong field ligands. They are called, sorry, not high field, they are called strong field ligands. Strong field ligands. And the weak field ligands always give high spin complexes. Weak field ligands always give high spin complexes. and the strong field ligands will give low spin complexes. Low spin complex. The splitting abilities of various ligands are arrived from the spectra of their complexes. Why these ligands are divided, how these are categorized is depending upon the spectra of these complexes. The ligands are arranged in the increasing order of the splitting ability. Here, the nature of the ligands are arranged in the order of the increasing order of the splitting ability. Ligands are arranged in the increasing order of their splitting ability. That is called a spectrochemical series. That is called a spectrochemical series. Now we will see how this series is actually. The first one is iodine, iodide, bromide, sulfur, thiocyanoligands, chloride, nitride, fluoride, OH, oxalate, water, ammonia, ethylene diamine, bipyridine. Then you have again nitrate, cyano and carbonyl. Okay, so the first ligands. The ligands are arranged in the increasing order of their splitting ability. That means these ligands have high splitting ability. Okay, greater splitting ability. So they are called strong field ligands. They are called strong field ligands. And these are weak field ligands. These are weak field ligands. The intermediate, there are some ligands which are intermediate. Okay, these are called intermediate field strength ligands. Field strength ligands. The order of increasing field strength of the common ligand is independent of the nature of the central metal ion. They are not depending on the what type of a central metal ion, whether it is a 5d orbital or 3d orbital or 4d orbital. No. It is their capacity or their power, whether they are belonging to the split, they are having the less splitting ability or they are having a greater splitting ability, are depending entirely on the nature of the ligands, not on the nature of the central metal atom. Okay, although this is the usual order, there are some changes will be always there. If the splitting of the d orbitals result from the point charges, we could expect that anionic ligands to exert the greatest effect. But most of these anionic ligands are weak field. We said that metal is centrally positive metal is an electropositive in nature, having a vacant d orbitals, making them available for the ligands to come and form a bond with them. So what we need? We need to ligands should be electron rich species. That means most of the time anionic ligands only should have a greater effect. But most of the time here you can see anionic ligands are in the weak field case. You can see here anionic ligands are the weak field ligands. Okay, but OH minus lies below the neutral ligand. OH minus is again the field strength is less even for the OH minus, whereas the H2O and NH3 neutral molecules have a greater splitting, they are saying. Okay, all these theories are explained in the adjusted crystal field theory. So there is another important theory which you need to learn is adjusted crystal field theory. Okay, so these are why OH minus is having more negative charge than the H2O and gives a lower d orbital splitting, and why Cn minus bipyridine and NO2 produce unusually high splitting but they are weak field. Okay, these observations may be understood qualitatively on the basis of the two types of bonding. Here in the most of the time the pi bonding has a major effect. Pi bonding, namely ligand to metal and metal to ligand back donation is possible. Okay, so that is the reason why what we decide is that anions should be more an electron splitting, they should produce more splitting capacity, but most of the time positive ions are only producing most splitting ability, because there is another concept is called that is pi bonding, namely ligand to metal and metal to ligand pi bonding. That is the reason why some anions remaining in the weak field and some positively charged ions are having high magnitude of splitting is very high for them. Okay, that reasons we will be discussing when I explain to you adjusted crystal field theory. Thank you.